Dear students, welcome to the 6th online class of Control System Engineering. In last class, we studied about how to find transfer function for complex translational mechanical system and how to find transfer function for complex translational mechanical system and rotational mechanical systems. The complex translational mechanical system were just like a multi-loop or a multi-node based electrical network. As these multiple node or a multiple loop based network requires more than one equation, similarly in complex translational mechanical system, more than one equation is required to define the dynamics. Then we studied about degree of freedom. For degree of freedom, we have to find how many test point or point of motion exist in a system. A point of motion in a system will be defined as a such point which can move freely while all other points of motion are held stationary. And number of these test points or these point of motion will be equal to degree of freedom, and also will define number of equations required to define dynamics of a system. Then we studied about the rules which we will use to find transfer function of translational mechanical system. Then we studied inspection method in which we generalize equations of motion. Then we studied rotational mechanical system and the passive linear components like spring, viscous damper and inertia, their torque to angular velocity relation, torque to angular displacement relation, and studied about their impedances. After this, we defined the rules which were quite similar to those of translational mechanical system. Dear students, by the end of this lecture, you will be able to find transfer function for linear time invariant rotational mechanical systems. Students, in this lecture, we will study about rotational mechanical system and we will also give an introduction to system with gears, and also will study effect on mechanical impedances driven by gears. Students, now we will study inspection method to find system of equations for a system with degree of freedom equals to. From the last example studied in previous lecture, we have two equations for a system with degree of freedom equals to. If we look at the equation, all the impedances which were directly connected to the motion of theta 1 make first part of equation, which is sum of impedances connected to the motion of theta 1 multiplied by theta 1 of s. The second part of equation includes mechanical impedances of those components which are common between theta 1 and theta 2. So in equation we will have subtracting sum of impedances between theta 1 and theta 2 multiply by theta 2 of s, and this will be equal to sum of externally applied torque at theta 1, which in this case is equal to T of s. Now coming to second equation, which belongs to second test point theta 2. All the impedances or sum of impedances connected to the motion of at theta 2 multiply by theta 2 of s, subtracting sum of impedances common between theta 1 and theta 2 multiply by theta 1 of s will be equal to sum of applied torque at theta 2. Now if we compare this with our second equation, J2, D2 and K are attached with the motion of theta 2 directly, whereas spring with coefficient K is connected between both nodes. So this will be our generic form of equation which we will use to find system of equation for inspection method. Dear students, now with the help of example, we will find out equations of motion by inspection method. In this example, we have a system which consists of one spring with coefficient k, three inertial components with coefficient j1, j2 and j3, and three viscous damper with coefficient d1, d2 and d3. If you look at the arrangement, one end of d1 and d3 is tied to a fixed wall, so they can't move, where j1, j2 and j3 have 3 points which can rotate freely. So we have a system with degree of freedom equals 3. First point of rotation is represented by theta 1 of t. Second point of rotation is represented by theta 2 of t. And last point of rotation is theta 3 of t. Students, now we will study a generalized form for a system having degree of freedom equals 3. For first test point, equation will be like sum of impedances connected to the motion at theta 1 multiplied by theta 1 of s minus sum of impedances between theta 1 and theta 2 multiplied by motion of second test point, which is theta 2 of s, subtracting sum of impedances common between theta 1 and theta 3 multiplied by motion of third test point, which is theta 3 of s, and this will be equal to sum of applied torque at theta 1. Second equation will be like sum of impedances directly connected to the motion at theta 2 multiplied by motion of second test point, which is theta 2 of s, minus sum of impedances common between first test point and second test point, means theta 1 and theta 2 multiplied by motion of first test point theta 1 of s, minus sum of impedances between second test point and third test point, means theta 2 and theta 3, and this will be multiplied by motion of third test point, which is theta 3, and this will be equal to sum of applied torques at theta 2. For third equation, all the impedances or sum of impedances connected to the motion at theta 3 multiplied by motion of third test point, which is theta 3 of s, minus sum of impedances between theta 2 and theta 3 multiplied by motion of second test point, which is theta 2 of s, minus sum of impedances common between theta 1 and theta 3 multiplied by theta 1 of s, and this will be equal to sum of applied torques at theta 3. Dear students, now we will use generalized form studied in previous slide to find out equations for this system. Using generalized form, we have 3 equations for this system. If you see, there is no common component between the motion point theta 1 and third test point theta 3. So you will see a coefficient of 0 in first equation and third equation. The externally applied torque occurs at test point theta 1, so it will appear in first equation. For rest of the equations, rules are same. Dear students, now we will study transfer function for system with gears. Gears are used in rotational mechanical system and allow us to make Variations between speed and torque. In some systems, we require more speed and less torque, where in some cases we require more torque and low speed. If you see the example of car, if you are driving a car in first gear, there will be more torque but a low speed. But if you are driving a car in fourth or fifth gear, your car will be moving at a high speed, but it will have a very low torque. Now we will study how to find transfer function for such systems. You may have observed or experienced a knocking sound from gears. This happens when two gears are loosely fitted, and this phenomena is known as backlash. We will study this in the section of nonlinearities. Now to find transfer function for system with gears, we'll assume that our system has no backlash. Dear students, a linearized model of a gear system is given in the figure. We will make analysis of this system and try to develop various relations for torque, angular displacement, number of teeth of a disk, and a radius of a disk. The input gear has a radius of R1. The number of teeth are represented by N1. The angular displacement covered is θ1, and externally applied torque is T1. The output gear has radius R2. Teeth are represented by N2, and the angular displacement θ2 is covered due to delivery torque T2. Now we will develop relations for these quantities for both gear 1 and gear 2. Students, now we will develop various relations for this gear system given in figure. When we apply external torque at gear 1, it will rotate in clockwise direction as gear 1 is connected with gear 2 with the help of teeth. Now if gear 1 will rotate, automatically it will rotate gear 2 or our output gear. The angular displacement will be represented by θ2 and the delivery torque will be equal to T2. But gear 2 will rotate in anti-clockwise direction. Now first point is the distance traveled along each circumference is the same. The distance traveled by first gear will be equal to distance traveled across second gear. For this, if you look at the second figure which represent arc length, it shows that arc length S is equal to radius multiplied by angle covered. Now both gear discs have same distance traveled, so S1 will be equal to S2, which implies that R1 θ1 will be equal to R2 θ2. The next point is the ratio of number of teeth along the circumference is equal to ratio of the radii of both discs. And the ratio of angular displacement of gears is inversely proportional to ratio of number of teeth. Dear students, further we will assume that gears of the system are lossless, which means energy applied to the gear 1 will be equally transferred to gear 2. The translational energy is force multiplied by displacement, where rotational energy is torque multiplied by angular displacement, and we'll obtain T1 theta 1 will equals to T2 theta 2 because gears are lossless and energy is completely transferred from input gear to gear. Combining all the relations we have studied, we conclude that ratio of torques T1 over T2 is same as ratio of radii of disk, which is R1 over R2, is equal to ratio of teeth along the circumference, which is N1 over N2, and these relations are inversely proportional to angular displacement ratio, which is theta 2 over theta 1. In figure you can see transfer function for angular displacement in lossless gear and for torque in lossless gear. Dear students, next topic is effect on mechanical impedances driven by gears. To understand this, see the figure in which a rotational system is given which is driven by gears. In this system, input torque or applied torque T1 of T is applied at input gear whose number of teeth are represented by N1. As input gears rotate, it with itself rotate output gear having number of teeth represented by N2, and the angular displacement covered is represented by theta 2 of T. Now we will study what impedance is experienced by input torque T1. For this, we will find a system without gears. Means we will shift all the impedances of the system to the input side of the system, where angular displacement is represented by theta 2 of T. Dear students, to study effect on mechanical system driven by gears, we will reflect the impedances from output part of the gears to input part of the gear. If you look at figure 1, it represents original rotational mechanical system driven by gears. For this reflection, we will start by writing an equation for output part of the system, which will be equal to J square plus Ts plus K multiplied by theta 2 of S, and will be equal to torque 2 represented by T2 of S. Now torque T1 can be reflected to the output by multiplying gear ratio N2 over N1. If you see T1 over T2 is equal to N1 over N2, we rearrange it to find the value of T2. So output torque T2 in terms of T1 will be equal to ratio of N2 over N1 multiplied by T1. The system having reflected torque can be represented in T2, and its equation is also highlighted here. Students, now we will find output angular displacement theta 2 of S in terms of input angular displacement theta 1 of S. From the equation of previous slide given here, in this we will replace theta 2 of S. With the help of equation, we know that theta 2 over theta 1 is equal to the N1 over N2. Replacing this in the equation, we will get our desired equation in terms of input angular displacement theta 1 of S and input applied torque T1 of S. And this will reflect all the impedances from the output to input
of the system. If you look at equation, all the impedances which belongs to output side are present at input side, but they are multiplied by the squared ratio of n1 over n2, where n1 represents number of teeth on input gear and n2 represent number of teeth on output gear. The transformed system after reflection is represented in figure. Dear students, now we will generalize the result from previous example. All the rotational mechanical impedances which are reflected through the gear trains are multiplied by a ratio which is number of teeth of gear on destination shaft divided by number of teeth of gear on source shaft whole square. If you see the figure 1 is our original system, where in figure 2 we have a transformed system. In figure 2, all the impedances from the load side or output side are transformed into input side. If you see the impedances, inertia J is present at the load side. At input side, inertial impedances is J multiplied by teeth ratio square. Similarly for damper and spring, both are multiplied by teeth ratio square. Dear students, now we will study with the help of example how to reflect the impedances. In this system, you have to find transfer function theta2 of s over t1 of s. Dear students, now we will start the solution. First step will be replace the passive elements with their impedances. Then we will define degree of freedom. For this system we have degree of freedom equals 1. As you can see in figure, both systems are connected with the help of gears. If any point on input side rotate due to torque, it will also rotate the second or output system. So this system have degree of freedom equals 1. In this problem, we have to find transfer function theta2 of s over t1 or input torque. So we will reflect the impedances J1 and D1 present on input side to the output side. For this reflection, we will multiply both impedances J1 and D1 by teeth ratio square, which is n2 over n1 whole square. Now T1 torque will be reflected by multiplying its ratio n2 over n1. This reflection of impedances and torque can be seen in the figure. Now equation of motion can be written as J equivalent s square plus D equivalent s plus K equivalent whole multiplied by theta2 of s, and will be equal to input torque T1 multiplied by teeth ratio, where J equivalent or equivalent inertial impedance will be J1, which is inertia of input side multiplied by teeth ratio square, which is n2 over n1 whole square plus J2, which is inertia of output side. Similarly, D equivalent will be viscous damper present at input site multiplied by teeth ratio square plus viscous damper coefficient d2 of output site. If you see the figure of original system, we don't have any spring component at input site, so K equivalent at output will be equals to K2. Now solving this equation for our desired transfer function theta2 of s or T1 of s, we will get G of s equal n2 over n1 whole divided by J equivalent s square plus D equivalent s plus Ke. And this can be represented in block diagram form where input is T1 of s and output is theta2 of s. Now if any of you have any questions, please ask. Dear students, welcome to the 7th online class of Control System Engineering. In previous class, we studied how to find equations of motion for a system with the help of inspection method for a degree of freedom equal to or a degree of freedom equal 3. Then we studied transfer function for system with gears. In this we studied various relations for torque, angular displacement, radius of the disk, and number of teeth along circumference of the disk. Then we studied effect on mechanical impedances driven by gear. In this we analyzed how we can reflect impedances from input to output or output to input by just multiplying gear ratio square. And this ratio is number of teeth of gear on destination shaft divided by number of teeth of gear on source shaft whole square. Dear students, after completing this lecture, you will be able to find transfer function for system with gears, with or without gear losses, and also we will study how to find transfer function for electromechanical systems. Students, contents of this lecture are: we will study transfer function for gear trains, and then we will study how to find transfer function for gears having losses. Then we will start electromechanical system, in which we will study DC motor, its transfer function, mechanical load analysis, and a dynamometer test. Dear students, now we will start gear train. A gear train is used to eliminate gears with large radius, or a gear train is used to implement the gear ratio by cascading smaller gear ratios. In this replacement of a large radius disk with multiple small radius gears requires the gear ratio must be the same. In the figure, a gear train is represented. With the help of gear train, we can introduce variation between speed and torque of the system. Like if you see an example of bicycle or a car, with changing the gears, we can make variations in the speed and torque of a system as per requirements. Now students, the schematic diagram of gear train is represented, where angular displacement covered by input is theta1 of t. Then second gear is having angular displacement of theta2, which is equal to the ratio of n1 over n2 multiplied by theta1. The third stage is having angular displacement of theta3, which is equal to the product of ratios of n1 over n2 and n3 over n4, and this whole multiplied by theta1. At fourth stage, angular displacement is theta4, and is equal to the product of ratios of n1 over n2, n3 over n4, and n5 over n6, and this whole multiplied by theta 1. And with this gear ratio, we can introduce changes in the speed or torque. Dear students, now we will find transfer function for a system with gear trains having losses. In previous examples, we were considering that gears are lossless, but now in this case, these gears will be having some inertial or viscous damping components. In this example, we have to find transfer function theta 1 of s over t1 of s. Now if you look at the figure, this system consists of 3 stages. The input torque is applied at first stage. Angular displacement of first shaft is theta 1 of t. It is connected with gears n1 and n2. At second stage, angular displacement will be theta 2. At third stage, we will be having angular displacement of theta 3, which is having an inertial load of J5. Second stage and third stage are connected with gears N3 and N4. Now J1 and D1 are inertial and damping components of first gear. J2, J2, D2 are inertial and damping components of second gear. Third gear is having only inertial component, which is J3, and fourth gear is having inertial component, which is J4. For our desired transfer function theta 1 of s over t1 of s, first of all we will find mechanical impedances in Laplace domain, and then we will reflect all the impedances to the input shaft having angular displacement of theta 1. Dear students, if you look at figure 1, we know that gear ratios are not same for all mechanical impedances, and we have to reflect all the impedances of stage 2 and stage 3 to the input side. So mechanical impedances of second stage are D2, J2 and J3. They will be reflected to first stage by multiplying gear ratio square, which is n1 over n2. Now the impedances of third stage, which include J4 and J5, first they will transfer to second stage by multiplying gear ratio square n3 over n4, and then they will transfer to first stage by multiplying n1 over n2 whole square. The result of reflecting all the impedances to input stage is represented in figure 2, having input torque T1, angular displacement of theta 1, with equivalent inertial component represented by JE and equivalent damping component represented by DE. Students, after reflecting the impedances and finding a figure for equivalent system, now we will find transfer function. After finding the rules of transfer function for rotational mechanical system, we will be having equation of motion for this system, which will be JES square plus DES plus theta 1 of s and will be equal to T1 of s. Now J equivalent is equivalent inertia of stage 1, stage 2 and stage 3, where equivalent damping constant dE is equivalent of viscous damping components d1 and d2. Our transfer function will be G of s equals theta 1 of s over t1 of s, and this can also be represented in a block diagram form, where t1 is input torque and theta 1 is angular displacement covered, where J equivalent and D equivalent are equivalent impedances experienced by Input torque. Dear students, our next topic is electromechanical systems. These are hybrid systems and made up of electrical and mechanical systems. In these systems, either we have electrical input, mechanical output, or mechanical input, electrical output. Various examples are antenna azimuth position control system, robots control, sun and star tracker, computer tab, disk drive position control system. Very common example in our real lives are fan, in which we have electrical input and a mechanical output. Dear students, now under electromechanical system, we will start a DC motor. In this we will find out how to find a transfer function for a DC motor. DC motor is an electromechanical system which gives us displacement output when voltage is applied. So in this we have electrical input and mechanical output. Now we will study how to find transfer function for this electromechanical system with the help of schematic diagram given in figure A, and we will represent transfer function in block diagram form as shown in figure B. Dear students, for transfer function, see the schematic diagram of a DC motor given in the figure. We have permanent magnets or stationary magnets in a DC motor which produces a magnetic field known as fixed field. Now as rotating circuit called armature through which the current IA of T flows passes through the fixed magnetic field at right angles and feel the force which is equal to magnetic field strength multiplied by length of the inductor multiplied by current passing through it. This force tends to rotate the rotor through which a torque is developed. The resulting torque turns the rotor and the rotating member of the rotor. Dear students, we also have a second phenomena that occurs in motor. As we studied earlier, when current passes through armature and armature is in fixed field, it produces a force through which it rotates. Now a conductor moving at right angle to magnetic field generates a voltage equals to magnetic field strength multiplied by length of conductor multiplied by velocity, and this voltage is produced at the terminals of the conductor, and the voltage produced at the terminal of the moving conductor is dependent on the angular velocity through which it is rotating, and this voltage is known as electromotive force or back EMF, which is directly proportional to the rate of change of angular displacement, and the proportionality constant is known as back EMF constant. Taking Laplace transform, we will get equation highlighted here. Further, we will use the relation that angular velocity omega m of t is equal to rate of change of angular displacement. Dear students, now to find relation between armature current, applied voltage and back EMF, we will replace passive electrical components with their impedances in Laplace domain, and then we will apply KVL, resulting in equation armature resistance Ra multiplied by current through it, impedance caused by armature inductance, back EMF voltage, and this will be equal to applied source voltage EA of S. Now we know that torque developed by motor is directly proportional to the armature current, and here proportionality constant is motor torque constant, which depends on the motor and magnetic field characteristics. In set of units, the value of motor torque constant and back EMF constants are equal. Students, now we have a loop equation from previous slide. In this equation, we'll substitute value of armature current and back EMF voltage. And with this, we will have an equation whose variable are torque, angular displacement, and input voltage. We are finding transfer function in terms of variable, angular displacement, theta m of s, and input voltage EA of s. Now to find torque in terms of angular displacement, we will study mechanical model of a DC motor, which consists of equivalent inertia at armature represented by Jm, and this includes both armature inertia and load inertia, which is reflected to armature. Viscous damping at armature is represented by coefficient dm, and this includes both viscous damping of armature and viscous damping of load, and which is also reflected to the armature. Students, here we have equation of motion for mechanical part of system, with which torque is equal to equivalent inertia of the motor multiplied by s square, damping constant dm multiplied by s, and theta m of s. Substituting this in the previous equation, we will get our desired equation whose variables are angular displacement theta m of s and input voltage E of s. Students, here we make an assumption that armature inductance is small compared to armature resistance, which is usual for a DC motor. So with this assumption, armature inductance equivalent to 0, we will further simplify the equation. And after little rearrangements, we will obtain our desired transfer function whose output is angular displacement and input is applied voltage. For further simplification purpose, the numerator of transfer function is made equivalent to constant k, where in denominator the terms without Laplace operators are made equal to constant alpha. And with this, our transfer function for DC motor will further reduce to the form k divided by s into s plus alpha. And this will be our desired transfer function whose input is applied voltage and output is angular displacement. In design process, through this we can measure for what type of input EA of s, what type of angular displacement will be covered by the DC motor. Dear students, now we will do mechanical load analysis for DC motor. In forming a transfer function for DC motor, we have used equivalent mechanical load, which is represented in figure 1. In this, equivalent inertia and equivalent viscous damping constants were used. Now we will explore what these equivalent quantities are. For this, look at the figure 2, which gives us DC motor driving a rotational mechanical load connected with the help of gears. The number of teeth along the circumference of input gear is represented by N1, where number of teeth on the circumference of output gears is represented by N2. The mechanical load consists of inertia JL and viscous damping coefficient DL. Now to find equivalent inertia at armature or equivalent viscous damping at armature, we will reflect both load inertia and viscous damping of the load to the armature side. For this reflection, we will use gear ratio square. So equivalent mechanical load experienced by DC motor will consist of equivalent inertia Jm and equivalent viscous damping constant dm, where Jm is inertia of armature and inertia of load reflected with the help of gear ratio square. Similarly, the equivalent viscous damping constant will be equal to viscous damping constant of armature and viscous damping constant of load reflected with the help of gear ratio square. Equations of both quantities, equivalent motor inertia and equivalent viscous damping constant, are highlighted. Dear students, we have studied various constants used in transfer function. Now we will study how to find values of these constants with the help of dynamometer test. For this test, we use torque and speed of a motor under the condition of constant applied voltage. For this relation, we will use equation given here, and we reach to this equation by applying KVL at electrical part of the DC motor, then substituting values of armature current and back EMF voltage, and then assuming that inductance of armature is negligible compared to resistance. As this equation is in Laplace domain, so we will take inverse Laplace transform to get time domain relation, and will reach to second equation of the slide. Now we assume that motor is operating in steady state with a constant DC voltage. So there will be no changes in torque and angular velocity of the DC motor when applied voltage is constant. So we will reach of the slide. Dear students, now we will solve the equation from last slide and will reach to equation which will relate motor torque with angular velocity, and graph of motor torque versus angular velocity is shown in the figure. For any constant applied voltage EA, we will be having torque to speed curve, and this plot is known as torque speed curve. Now to find the constant, we will find intercept of these curves. In the first equation of the slide, to find maximum torque or stall torque will occur if angular velocity is equal to 0, which means a system will apply maximum torque to rotate the motor, but due to limitations it will not move, and this torque is known as stall torque. And for second variable, we will assume that torque is equal to 0. Replacing this in the first equation, we will get maximum speed of the DC motor, and this will be equal to EA over KB, where T stall is equal to KT over RA multiplied by EA. Dear students, now we will find the constants from the relation of stall torque and no load angular speed. Rearranging both equations, we will get KT over RA, which is Motor torque constant over armature resistance will be equal to stall torque divided by applied voltage, and back EMF constant will be equal to applied voltage EA divided by no load angular speed of the DC motor. Dear students, now with the help of example, we will find transfer function for DC motor. With the help of data given in figure A and B, we have to find transfer function theta L over EA of S, which means the transfer function will relate angular displacement covered by a load when electrical voltage is applied to the DC motor. Students, we will start the solution by finding equivalent inertia and equivalent viscous damping for DC motor. Under the topic of mechanical load analysis, we have relations that equivalent inertia is equal to inertia of armature plus inertia of load multiplied by gear ratio square. Similarly, equivalent viscous damping constant is equal to viscous damping coefficient of armature plus viscous damping coefficient of load multiplied by gear ratio square. Substituting the values from the figure, we have equivalent load inertia is equal to 12 and equivalent viscous damping constant is equal to 10. Now we will find electrical constants using the torque speed curve given in the figure of example. From torque speed curve we have T stall is equal to 500, no load velocity is 50, and applied electrical voltage is 100 volt. Dear students, now after finding values of various quantities, we will find out electrical constant. Now from dynamometer test, from the relation of T stall, we have KT over RA is equal to T stall divided by EA, and this is equal to 5. Where from second part, which is no load speed, we have KB is equal to EA over no load angular velocity of DC motor, and this is equal to 2. Now we have transfer function for DC motor, which is theta m over EA. Substituting these values, we obtain a numerator of 0.417 divided by S into S plus 1.667, where the desired transfer function is load angular displacement divided by applied voltage. So for this we will use gear ratio and find out motor angle in terms of load angle. Substituting this, we will obtain our desired transfer function. Now N1 over N2 is equal to 1 over 10. So our desired transfer function load angle of DC motor divided by applied voltage will be equal to numerator of 0.0417 divided by S plus 1.667 whole multiplied by S, where S is Laplace operator. And this is our desired transfer function. This transfer function can also be represented in block diagram form, where input of the system is applied voltage EA of S, where output is load angle theta L of S. This can also be used for design purpose to analyze the load angle when various type of input signals are applied. Now if any of you have any questions, please ask. Dear students, welcome to the 8th online class of Control System Engineering. In last class we studied how to find transfer function for system with gears having gear train and gears with losses. Then we started electromechanical system. In this we studied about a DC motor, how to find transfer function for a DC motor, its mechanical load analysis, and its dynamometer test. Now we'll start lecture 8. Dear students, by the end of this lecture, we will cover final two objectives of modeling in frequency domain. This lecture covers analogous behavior of electrical and mechanical circuit. We will study how to linearize a nonlinear system in order to find its transfer function. Students, contents of this lecture are: we will start with electric circuits analog. In this we will study about series analog and then parallel analog. Then we will study about nonlinearities and linearization process. Dear students, so far in this chapter we have studied electrical systems and mechanical systems. Now we will start electric circuit analog. In this we will demonstrate that how the mechanical system we have studied can be represented with equivalent electric circuit. If you look at the figure in this, passive linear components of electrical network and that of translational mechanical components are given. In electrical networks we know that capacitor and inductor are energy storage, where resistor is energy dissipating element. In translational mechanical network, spring and inertia are energy storage element, where a viscous damper is energy dissipating element. We have studied equations for both systems. Now we will analyze that variable of electric circuits behave exactly as the analogous variables of mechanical systems. Using this commonality, we will produce electric circuit equivalent for mechanical system. Students, now we will start formally electric circuit analogs. An electric circuit that is analog to a system from another discipline, like mechanical system, is called an electric circuit analog, which means that we will having an electric circuit which will represent a system from another discipline, like it can be translational mechanical system or a rotational mechanical system. And this is done because the analogous behavior of variables is same. This can be done by comparing the equations defining dynamics of the system. Like if we have an electric circuit, we will find out equation for that. And second, we have a mechanical system, and we will find out equation for that system too. Then we will make comparison of the variables. And with this comparison, we will make our desired analog electric circuit. Electric circuit analogs are of two types. First is series analog and second is parallel analog. If mesh equations are compared with equation of system from another discipline, is known as series analog. When nodal equations of electrical network are compared with equations of system from another discipline, is known as parallel analog. Students, now we will study series analog. If you look at the figure, we have two systems. Figure A represents simple translational mechanical system, where figure B shows desired electrical representation of mechanical system. For system in figure A, equation of motion is represented in Laplace domain. If we apply KVL at figure B, its mesh equation is also highlighted here. Both equations are not directly analogous to each other because displacement and currents are not analogous. Student, now we will develop analog behavior by converting displacement into velocity, and for this we will divide and multiply left hand side of translational mechanical system equation by Laplace operator S. Now we can make comparison of both equation, and this comparison will be done with the power of Laplace operator S. Now our desired electric circuit analog is represented in figure C, where figure D shows analogous behavior of electrical and mechanical components. In this, mass M is represented by inductor, so their analogous behavior is same. A viscous damper ρV is represented by a resistor. A spring is represented by capacitor with capacitance equal 1 over k farads. Force applied to the system is represented by source voltage, and velocity of translational mechanical system is represented by mesh current. So with this, by analogously comparing the behavior of various components, we have made an equivalent electric circuit analog of our translational mechanical. Now we will study how to make electric series analog of a system from another discipline who is defined by more than one equation or degree of freedom is greater than 1. For example, in figure, a translational mechanical system is given with degree of freedom equals 2, and we have 2 points of motion. First is x1 and second is x2. Now for equivalent series analog, we will be having 2 mesh in the circuit, and all the impedances that are connected with M1 will appear in first mesh. All the impedances those are connected with M2 will occur in second mesh, and all the impedances that are common between M1 and M2 will occur in series form common to both mesh. Students, now if you look at the figure, M1 is directly connected with spring with coefficient K1, surface friction represented by rho V1, and applied force F of t. So these quantities will occur in first loop. M2 is directly connected with spring with coefficient K3, its surface friction with coefficient rho V2, and these quantities will occur in second mesh, where the components common between the motion of M1 and M2 are a spring with coefficient K2 and a viscous damper with coefficient rho V3. These will occur in series and will be common to the both meshes. Now we will start. Dear students, as we know that this system is example of translational mechanical system we have studied earlier, and from there we will use dynamic equation for the system. Now for making analog, we will convert displacement into velocity by multiplying and dividing left side of both equations by Laplace operator S. And this will give us our desired equation for comparison. And from these equations, we will form our desired series analog circuit. Dear student, now as we have converted equation of system into desired form, now we will make an electric analog circuit. As said,
All the impedances which are connected directly to the motion of first test point will occur in first loop. In this case, spring with coefficient K1, surface friction with coefficient rho V1 were connected with mass M1. These three quantities will appear in first mesh. Also, externally applied force is acting on mass M1, so it will also appear in first loop in the form of voltage source represented by F of t. The velocity of first test point will be represented as mesh 1 current V1 of t. Now for second test point or second loop, objects associated with M2 are a spring with coefficient K3, surface friction with coefficient rho V2, and its mass M2. These three quantities will appear in second mesh. Now the components common between M1 and M2, which includes a spring with coefficient K2, a viscous damper with coefficient rho V3. These will appear in the form of series common to the both meshes. And with this, our desired series analog of mechanical system will be formed. Students, next topic we have is parallel analog. For the system in given figure A, we will make a parallel analog as represented in figure B. Now for the same system, we have equation of motion in terms of velocity from the last example. For system in figure B, we will apply nodal law and find out nodal equation for this parallel RLC circuit. Dear students, now we will compare quantities of both equations corresponding to the power of Laplace operator S and form our desired circuit as represented in figure C of this slide. Upon comparison, we conclude that mass M of translational mechanical system in terms of nodal circuit can be represented with a capacitor with capacitance equals amp farads. A viscous damper with coefficient rho v can be replaced with a resistor with value of resistance 1 over rho v ohms. A spring of translational mechanical system with coefficient K can be replaced with an inductor with value of 1 over K henries. Applied force of translational mechanical system will act as a current source and its value will be equal to F of t. The velocity of translational mechanical system is equal to V of t will act as a node voltage in this conversion. And by this we have converted our translational mechanical system into a parallel analog electrical network. Dear students, now we will study how to make a parallel analog of electrical network for a system from other discipline which is defined by more than one equations or having a degree of freedom greater than 1. We will study this from the example of translational mechanical system given in the figure. Components which are associated with the motion appear as parallel elements connected to a node. Components of adjacent motion are drawn parallel electrical elements corresponding to two nodes. In the given example, we have a system with degree of freedom equals 2. The first point which can move is M1 Its motion is represented by x1 of t, Second test point which can move is m2 and its motion is represented by x2 of t. Components attached to first point are spring with coefficient k1, surface friction with the coefficient rho v1, Components connected with second test point are spring with coefficient k3 and its surface friction rho v3. For first node, mass m1, spring with coefficient k1 and surface friction rho v1 will be present as a parallel in first node. For second node, mass m2, spring with coefficient k3 and its surface friction rho v2 will appear as parallel to second node. Now the components common between m1 and m2, which includes a spring with coefficient k2 and viscous damper with coefficient rho v3, these two quantities will appear. Dear students, as this system is from last example, so we have its equation in force displacement form, and then after conversion, which includes multiplication and division of left side of both equation by Laplace operator S, will convert into a desired velocity force form. Now after obtaining equations in desired form, we will make parallel analog circuit for this translational mechanical system with degree of freedom equals 2. Dear students, now from the equation obtained in force velocity form, we will make our desired parallel analog of mechanical system, which is also shown in the figure. Now, as said earlier, this system has degree of freedom equals 2. Now in translational mechanical system, all the impedances which are associated with first test point will occur as a parallel to the first node. Here we have first node which is V1 of t. Now with first test point, impedances associated are a spring with coefficient k1 and surface friction with coefficient rho v1. So these three quantities, mass m1, spring k1 and surface friction rho v1, appear as parallel to first node. Now with m2, components associated are a spring with coefficient k3 and surface friction with coefficient rho v2. These three quantities, mass with coefficient m2, spring with coefficient k3 and surface friction with coefficient rho v2, will appear as parallel to the second node. Now the components common between m1 and m2, which includes a spring with coefficient k2 and a viscous damper with coefficient rho v3, both these components will be parallel to each other and will be common between two nodes. And with this, we will make parallel analog electrical network for a given translational mechanical system whose degree of freedom is 2.
Dear students, next topic we will study is nonlinearities. Most of the systems that belong to real life are nonlinear, and this course of control system engineering is based on controlling of linear systems. So for this, first we will study what are the properties of linear system which distinguish them from nonlinear systems. Linear system possesses two properties. First one is superposition and second one is homogeneity. The property of superposition says that if we have a linear system and we apply various inputs, let's say first we apply input R1 of t, for which system yields an output of C1 of t. Then we apply an input R2 of t, and for this system gave us an output of C2 of t. Now we apply a third input, which is sum of R1 of t and R2 of t. For this system output must be equal to sum of C1 of t and C2 of t. This is the linear property, and this property is also demonstrated in the figure. We have a linear system whose first input is R1 of t, for which we have output of C1 of t. Then we have input of R2 of t and output of C2 of t. Then we have an input which is equal to R1 plus R2 of t, and whose output is equal to sum of previous outputs, which is C1 of t plus C2 of t. Students, now we will study homogeneity property of linear system. This property says, for any linear system, if we have input R1 of t, this will give us an output of C1 of t. Second, if we multiply our input by any scalar, then our output will also be scaled by the same number. This is demonstrated in the figure. For a system having original input, we have a defined output. Now if input is multiplied by 2, our output is also scaled by 2. The property of superposition or additive and the property of homogeneity or scalar are observed in linear systems. Dear students, now with the help of example, we will study how to identify linear or a non-linear system. If you look at the figure, figure A represents graph for a linear system, where figure B represents graph for a non-linear system. Now in figure A, if you apply an input of 1, we have output of 0.5. If we have an input of 2, we have output of 1. And if we apply a third input, which is sum of previous two, means 1 plus 2 equals 3. For this, we must have output of sum of previous two outputs, which is 1 and 0.5 equals 1.5. And this is also clear from the graph that for an input of 3, we have output of 1.5. Or we can say that output is half times the input, or mathematically f of x is equal to 0.5 times x, where x is the input of the system. So this system fulfills the property of superposition principle. Students, now if we look at a graph B, in this input of 1 yields an output of 1.5, where input of 2 yields output of 1.8, and if we apply a third input, which must be 1 plus 2 equals 3, for this our output must be equal to 1.5 plus 1.8, which equals 3.3. But if you see the graph, its output is around 1.9. So this system is not following the property of superposition principle. Students, now for same system, we will check the property of homogeneity. For a property of homogeneity, input of 2 yields output of 1. Now multiplying the input by a scalar equals 2 gives an input of 4. For this input, we have output must be equal to 2. And from graph it is clear that for input of 4, our output is equal to 2. And certainly the property of homogeneity doesn't apply to figure B. So our system A is a linear because it fulfills both properties of linear system, where system in figure B is nonlinear. Dear students, now we will study some physical nonlinearities. In this we will study saturation, dead zone, and backlash. These physical nonlinearities are also represented in figure. First one we have is saturation. Saturation mostly occur in amplifiers. If you look at the graph of amplifier, for certain range of input, you will get an linear amplified output, but when you exceed the operating range, its output becomes saturated and system response is no more linear. And this occurs for high input voltages. Next physical nonlinearity we have is dead zone. Dead zone mostly occurs in motor. When we apply a low input voltage, then the desired excitation voltage, the motor output is equal to 0 due to frictional forces and no response from motor is achieved. So for certain range of input, system response or output is equal to 0. This nonlinearity is known as dead zone. Last one we have is backlash. Backlash occurs in system with gates. Sometimes you hear a knocking sound from the gears. This is because the gears are loosely fit or a gap exists between the gears. For a certain amount of time, the gears are disconnected as suddenly you change the direction of rotation. At the moment when gears are disconnected, though you apply the input, system do not respond, and this is known as. Dear students, now we will start linearization process to find out transfer function for a system. The electrical and mechanical systems so far we have studied, we assume that these are linear systems because transfer function exists for linear systems only. Now to find transfer function for a nonlinear system, we must linearize it. After writing nonlinear differential equation for the system, we will find out nonlinear component present in the equation. Then we will linearize it for small signal input about a steady state solution. In this actually, we limit the operation of a nonlinear system to specific range. And about this specific range, system behaves linearly. When this small signal input is equal to 0, the steady state solution is called equilibrium and is selected as second step in the linearization process. After identifying nonlinearity and equilibrium point of the system, in next step we linearize the nonlinear differential equation. After this, we take Laplace transform with zero initial condition to separate the input-output variables. And finally we reach to our desired transfer function. Dear students, now with the help of example, we will study the linearization process. In figure, a graph of a nonlinear system is shown, and this nonlinear system is operating at point A, and its values are x, f of x, f of x. You can see this in the figure. Now for linearization process, we will limit the operation of this nonlinear system to a specific range. Means a small change in input can be related to the small change in output by the way of slope of the curve at point A. Now the slope at point A is represented by MA. As system is operating at point x0, f of x, we will introduce a small change in input, which is del of x, and with this our new input will be x. The difference between x and x0 will be del x, where difference between f of x0 and f of x will be del f of x. Now using point slope form, we have a relation f of x minus f of x0 is approximately equal to the slope multiplied by x. And students, this will be reduced to the relation del f of x approximately equal to ma del of x. And this is our linear equation for the change in input to the change in output. And this can be further expanded here. The relation is shown graphically here, where we have set of new axes del of x and del of f of x at point A. And f of x is approximately equal to f of x0, the ordinate of our new origin, plus small changes, which is slope ma multiplied by del x away from the point A. Dear students, the linearization process we studied earlier can also be performed using Taylor series expansion. In this, the value of a function in terms of the value of that function at particular point, the excursion away from that point, and the derivatives evaluated at that point. Taylor series is given here. Now we said that for linearization, we will use small changes in input. So higher order terms can be neglected with this. The resulting approximation yields a straight line relation between changes in function and excursions away from the x0. Now neglecting the higher order terms, we get desired form, which is similar to the previous case. Now changes in functional value are approximately equal to slope at that particular point multiplied by change in x. This is a linear relationship between del f of x and del x for small excursions away from x0. Dear students, now we will study with the help of example how to linearize a nonlinear ordinary differential equation of a system. If you analyze the given ordinary differential equation, the given system is nonlinear due to presence of cos function in its ODE. Now we will linearize it about the point x equals pi by 4. As the process begins by introducing small change in input, so here we suppose x equals del x plus pi by 4, where del x is small change about pi by 4. Now substituting the value of x in the ordinary differential equation, we get second equation of the slide. But we know that derivative of constant is equal to 0. So the terms involving double derivative of del x plus pi by 4 divided by del t square will be equal to double derivative of del x, and derivative of del x plus pi by 4 will be turned into derivative of del x. And for this limited region of operation, we will be having ODE given below. Now the nonlinear term cos of x can be linearized with the help of Taylor series as discussed in next slide. Students, the nonlinear term in this ODE was cos of x, and the equilibrium point about which we have to linearize it is pi by 4. Now we will use truncated Taylor series. And here f of x equals cos of del x plus pi by 4, where f of x naught will be equal to f of pi by 4 and x minus x naught equals del x. And now substitute these values in the first equation of the slide. Now solving for cos of del x plus pi by 4, we get cos of del x plus pi by 4 equals f of x naught, which is equal to cos of pi by 4 plus slope, which is minus sine pi by 4 whole multiplied by del x, and this is equal to square root of 2 divided by 2 minus square root of 2 divided by 2 multiplied by del x. Substituting this in the ODE obtained, we get our desired linearized differential equation of the system, and this ODE is valid for that specific region around pi by 4. Now if any of you have any questions, please ask. Dear students, welcome to 9th online class of Control System Engineering. In this class, we will start chapter 3, which is Modeling in the Time Domain. In first lecture of Control System Engineering, we have discussed the course flow, which starts from mathematical modeling of a physical system. Then from mathematical model or ordinary differential equation, we will find out transfer function or state space model. Now we will study how to find state space model of a system. Dear students, as discussed in chapter 2, in classical control, we analyze a system in frequency domain or Laplace domain, where in modern control, we study or analyze a system in time domain. Dear students, by the end of chapter 3, which is modeling in time domain, you will have skill to represent mathematical model or dynamics of any linear time invariant system in the form of state space representation. By the end of this chapter, we will also study how to represent electrical and mechanical system in state space form. Dear students, now coming to the contents of this lecture, we will start from the definition of a state space. What is a state variable, a state vector, state equation, and output equation. Then we will study transfer function versus state space. And finally, we will study how to make a state space representation for any given physical systems. In the given examples, we will study how to make state space representation for electrical network and translational mechanical system. Dear students, state space is a mathematical representation of any physical system. This mathematical representation includes set of input, output, and state variables. So basically, for a state space representation, we have two equations. First equation is known as state equation, where second equation is known as output equation. Dear students, as you are familiar with input and output, now we will study state variable. A state variable is a set of parameters or variables which provide sufficient information about the system at any instant of time, or any variable that responds to an input or initial condition in a system. For example, consider we have a translational mechanical system. In this, displacement of a body is a state variable. In an electrical network, charge flowing through the components is a state variable, and the angular velocity in rotational body is a state variable. These variables provide information about the system at any instant of the time. State variables are identified from the system under consideration, and these variables should be dynamic in the system. State vector. A vector who is formed by state variables is known as state vector. Students, now we will study state equation and output equation. These both equations combinedly form state space representation of a system. First is state equation. A set of simultaneous first order differential equation of state variables is known as a state equation. As studied, a state variable is a set of parameters which provide sufficient information about the system, and these variables must be dynamic in the system. So when these variables are represented in first order differential form, this is known as state equation. Next is output equation, an algebraic equation that expresses output variables of a system as linear combination of state variables and inputs. In these equations, x is a state vector, x dot is derivative of state vector with respect to time, y is output vector, u is input or control vector, a is system matrix, b is input matrix, c is output matrix, and d is feed forward matrix, and mostly feed forward matrix is 0. If you look at the figure, it represents state space representation of two states. One is VR and second is VC. The curve represents trajectory of a state vector. The first state vector we have is x of t. As time increases or system start its movement, its states also get changes, and these changes are represented in the form of curve. And x4 represents state vector at time instant t equal to 4 seconds. Dear students, now we will discuss some basic differences between transfer function and state space. Transfer function is relation between input and output, or it is a ratio of input divided by output. It helps us to analyze a system in frequency domain, where state space involves input, output, and state variables, and it is represented by state equation and output equation. In this, we analyze a system in time domain. Dear students, with the help of state space, we can represent dynamics of a physical system in time domain. For this representation, some steps are followed as discussed below. For state space representation, first of all we will identify all the dynamic variables which give sufficient information about the system at any instant of time. And these variables will be termed as state variables. In second step, we will represent this state variable in the form of first order differential or difference equation known as state equation. Let we have system of nth order. For this, n state variables of the system will be represented in n first order simultaneous differential equation. Now for given initial conditions and input to the system, we can solve the simultaneous differential equation for the state variables and can find out behavior of a system for any time instant greater or equal to initial or start time, which is t naught. After solving these state equation, we can obtain output of the system as combination of input and state variables. And these equations are known as output equation. The set of combination of state equations and output equation form a state space representation for any physical system. Dear students, as an example, a linear time invariant second order system is represented in state space model where x1 and x2 are its state variable, a single input v of t. In first equation, x1 derivative is equal to linear combination of states and input. In second equation, first derivative of x2 is equal to linear combination of states and input, where output equation is linear combination of states and input. Now with the help of example, we will study how to form a state space representation for any system. In the given example, we have to make a state space model for an RLC network. Dear students, first step in analysis of any system is to find out ordinary differential equation defining dynamics of that system. For this RLC network, first of all we will write KVL equation, which is first equation of this slide. Now we will identify state variables for this RLC network. As we know, we can replace current by charge using the relation current is equal to rate of change of charge. And we get second order differential equation for the system. Now for this system, we have two state variables. First one is charge and second one is current. Now after identifying state variables, we will write these state variables in the form of first order differential equation. Dear students, now we will represent state variables of RLC network as first order derivatives for state equations. Our first state variable is charge flowing through the circuit, and second state variable is current flowing through the circuit. We know that current flowing through the circuit is equal to rate of change of charge, or we can say that rate of change of charge is equal to the current. Through this we obtain our first differential equation. Now for first order differential equation of current, we will use KVL equation of the circuit. This equation, integral of current will be replaced by charge. Then terms involving derivative of current will be on one side of equation, and all other terms will be shifted to other side of the equation. And with this we will get second equation for state model. Now both the equation involving terms first order derivative of state variable represent state space model for the system. Students, we are observing voltage drop across inductor as a output of the system, and its relation can be obtained through KVL. State space model of linear time invariant system can also be represented in matrix form, which is x dot equals ax plus bu, where A is system matrix and B is input matrix. These matrices contain coefficients of state variables and input from first order set of differential equations. Here x is state vector, which includes charge and current, and x dot represents rate of change of state variables with respect to time, and u is input of the system. Now output of the system can also be represented in matrix form, where y equals cx plus du, where c is output matrix and d is feed forward matrix. Dear students, here in another example of RLC network, we have to make state space representation where output is the current through the resistor. In the solution of this example, at first we will label all the branch currents. This includes current through the inductor, which is represented by IL, current through resistor, which is represented by IR, and current through capacitor, which is represented by IC, as shown in figure. Now we have to find out state variables for this system. In this system, current through the inductor and voltage across capacitor are our state variables, and this is obtained by writing derivative equation for all energy storage elements. Now we know that current through capacitor is equal to capacitance of capacitor multiplied by rate of change of voltage. Voltage across inductor is equal to inductance of inductor multiplied by rate of change of current flowing through it. Now both these equations represent first order derivative of our state variables, but in state equations, first order derivative of state variable is equal to linear combination of states and input. Now to complete this state model, we will use Kirchhoff voltage law, Kirchhoff current law. Dear students, now we will apply KCL or KVL to complete our state equations model. Now if we apply Kirchhoff's current law at node 1, we obtain current through the inductor is equal to current through resistor plus current through capacitor. And from this current through capacitor will be equal to minus current of resistor plus current through the inductor, where current through resistor is equal voltage across resistor divided by resistance of resistor. As resistor and capacitor are in parallel, so voltage across capacitor is equal to voltage across resistor. Now we will apply KVL at outer loop, from which source voltage will be equal to voltage drop across inductor and voltage drop across capacitor. And from this, voltage drop across inductor will be equal to minus voltage across capacitor and source voltage, which is V of t. Now substituting these values in derivative equation for all energy storage elements and making rearrangements, we will obtain our desired state equation model for the system. Dear students, now with rearrangement, we will obtain our state equation model for the system. Now for output, we know that current through resistor is output of the system, and the current IR is equal to voltage across resistor, which is also equal to Vc divided by resistance of resistor. Now the equation 3.27a, 3.27b and 3.28 completes the state space representation for this RLC network. As this RLC network is made up of linear components, so this state space model can also be represented in matrix form. Equation 3.29a represent state equation model in matrix form, where equation 3.29b represent output equation in matrix form. Dear students, now with the help of example, we will find state space model for a translational mechanical system. Dear students, in this example, we have two masses M1 and M2 lying on a frictionless surface. M1 is connected with viscous damper D, and M1 and M2 both are connected through a spring with coefficient K. Motion of M1 is represented by x1, where motion of M2 is represented by x2. Externally applied force act on mass M2. This system has degree of freedom equals 2. So we will obtain our desired equations of motion following the rules or steps related to translational mechanical system discussed in chapter 2, and both equations are given here. Dear students, now for state space representation of translational mechanical system, we have to identify the state variables. For these state variables, we will analyze the system. As the system consists of two masses, M1 and M2, and both masses are moving in the given direction of motion. M1 is moving in the direction of x1, where M2 is moving in the direction of x2. Now in general, whenever we apply a force on any object, and with this movement, this object covers some displacement. During the time at which it is moving, it has some velocity and also it has some acceleration. So students, these three variables are associated with motion of an object. Now if we look at the relation between these variables, we know that Rate of change of displacement is velocity. Rate of change of velocity is acceleration. And as a rule, we have to choose minimum number of variables for the state space model of a system. So here x1 is representing displacement covered by mass 1 and its derivative, which is dx1 over dt, will represent velocity or v1. Now rate of change of velocity will be acceleration, which is equal to double derivative of displacement x1. So x1 and v1 will be two state variables for mass m1, which will be representing displacement, velocity and acceleration. Now for m2, its displacement will be represented by x2 and its derivative, which is dx2 over dt, will represent velocity. For velocity, we will also use variable v2. So v2 equals rate of change of x2. Now acceleration of mass 2 will be rate of change of velocity or double derivative of x2. So x2 and v2 will be state variables for mass 2, which will be representing its displacement, velocity and acceleration. Dear students, equation 3.44 and 3.45 defines equations of motion for this system. Now we will substitute state variables for both masses m1 and m2 and their differential relation into equations of motion 3.44 and 3.45, and with rearrangements we will get our desired state equations, which are from 3.46a to 3.46d. As this system is linear, so we can also represent its state space form in vector matrix form, given in equation 3.47. Now if any of you have any questions, please ask. Dear students, welcome to 10th online class of Control System Engineering. In previous classes, we have discussed how to develop mathematical model for different physical systems, also expressing their differential equation in terms of transfer function using Laplace transform, and expressing their differential equation in terms of state space model. And the systems mostly studied were electrical networks, translational mechanical, rotational mechanical, and electromechanical. Dear students, now we will study time response of any physical system, which is CLO3 of this course. Dear students, in this chapter of time response, you will study how to find time response of a system from poles and zeros of the transfer function. You will study about transient response of first order system and will write general response of second order system given the pole location. You will find the damping ratio and natural frequency of second order system, also the transient specifications, which include settling time, peak time, percent overshoot and rise time for underdamped second order system. Dear students, now coming to contents of this lecture. In this lecture we will study poles, zeros and their effect on system response. Then we will start first order systems, in which we study about their transfer functions, time constants, rise time and settling time. Dear students, output response of a system is the sum of two responses. One is forced response and second is natural response. Now, natural response is due to transfer function or due to the poles of the system, where forced response is due to input of the system. Now, if we have output response relation in frequency domain, then we can find time domain response with the help of inverse Laplace transform. But this conversion from Laplace domain to time domain is time consuming. So we are looking for a method through which we can find result in minimum span of time. For this, we will use poles, zeros and the relationship to the time response of the system. Dear students, now we will study poles and zeros of a transfer function. Starting with poles, the values of the Laplace transform variable s that cause the transfer function to become infinite, or any root of denominator of transfer function that are common to roots of the numerator are known as poles. In the similar way, the values of Laplace transform variable s that cause the transfer function to become 0 or any root of the numerator of transfer function that are common to the roots of denominator are known as zeros of transfer function. Dear students, now with the help of example, we will study system response with the help of poles and zeros. In the given figure A, we have a system whose transfer function is s plus 2 divided by s plus 5, and input applied to the system is step, which means that R of s is equal to 1 over s. Figure B shows pole 0 plot of the system. In this we have a pole at -5 and a 0 at -2. Now we want to find output or system response, which is equal to transfer function of the system multiplied by input, which means G of s into R of s, and this will be equal to s plus 2 divided by s into s plus 5. Now for the response of the system in time domain, we will use partial fractions, and this will be equal to a divided by s plus b divided by s plus 5. Now solving for the values of a and b, c of s will be equal to 2 divided by 5 whole divided by s and 3 divided by 5 whole divided by s plus 5. Now using the rules of Laplace transform table, we will get our desired system response in time domain, which is c of t will be equal to 2 over 5 plus 3 over 5 multiplied by e power minus 5t. Dear students, same example can also be studied with the help of pole 0 plot. Figure A represents the original system with transfer function s plus 2 divided by s plus 5. Input of this system is step, which is equal to 1 over s. Figure B shows pole 0 plot of transfer function of the system. In this plot, we have a pole at -5 and a 0 at -2. Now if you look at figure C, in this we have 3 pole 0 plot. First plot represent pole of input which is at origin. Second plot represent 0 of the system which is at -2. And the last plot represent pole of the system which is at -5. If you look at output transform equation, this equation is sum of two terms. One is having a denominator equal S, which represent input pole. Second term represent denominator S plus 5, which represent system pole, and numerators of both the terms are defined by zeros and poles of the system. Now if we look at time domain response, C of t equals 2 over 5 plus 3 over 5 e power minus 5t. If you take inverse Laplace of 2 over 5 divided by s, we get 2 over 5, and this part was due to the input pole, so this will be our forced response of the system. In second term, we were having 3 over 5 whole multiplied by 1 over s plus 5. Now if we take inverse Laplace of 1 over s plus 5, we get e power minus 5t. So this portion e power minus 5t due to system response or pole of the system, and this will be our natural response of the system. Dear students, now we will summarize last slide here. The first point is the pole of the input function generates the forced response of the system. In this, a pole at origin generated a step function at the output. Secondly, the pole of the transfer function generates natural response of the system. In this, the pole at -5 generated e power minus 5t. Third one is, if we have a pole minus alpha on the real axis of S plane, this will generate an exponential response of the form e power minus alpha t. And as you move pole to the negative side of the real axis, the response of the system will become faster and exponential transient's response will decay to 0. Last one is the zeros and poles generates the amplitude for both forced response and natural responses, which we have find out in partial fractions calculation in A and B. Students, in the given example, we have a system. For this, we have to find out output equation C of t in terms of forced response and natural response. If you look at the figure which defines a system with 3 poles, one is at -2, other is at -4, and the last one is at -5, and a 0 at -3. Input of the system is step. Now we know that poles of the system generates exponential part as a part of natural response, and the pole of input generates forced response. So the given output transform equation will consist of 4 terms. First term will be due to input pole, and this will be our forced response. Second, third and fourth terms of the partial fraction will be due to poles of the system, representing pole at -2, pole at -4 and a pole at -5. These three terms combinedly will form natural response of the system. Now taking inverse Laplace, we'll have C of t equals k1 plus k2 multiplied by exponential power minus 2t plus k3 multiplied by exponential power minus 4t plus k4 multiplied by exponential power minus 5t. Here k1 will be our forced response, where terms with coefficient k2, k3 and k4 will be our natural response corresponding to the pole at -2, -4 and -5 respectively. Dear students, now we will start first order systems. In this topic, we will discuss time response of first order systems and transient characteristics associated with the response of first order system. Students, transfer functions of the system with a single pole are known as first order systems. In this topic, we will study transfer functions of first order system without zeros. If you look at the figure A, the system in figure A is represented by transfer function g of s, which is equal to a divided by s plus a. Means the system is having a single pole. Input of system is r of s, where c of s is output of the system. Figure B represent pole zero plot of the first order system. Now if we assume that step input is applied to the first order system g of s, then output of the system C of s will be equal to R of s multiplied by G of s, where R of s is equal to 1 over s and G of s is equal to a divided by s plus a. Now using partial fraction, we will find output transform equation, and then we will take inverse Laplace transform to get C of t, where C of t equals 1 minus e power minus at, or sum of forced response plus natural response. Here natural response is equal to minus e power minus at, or the response due to the pole of the system, where forced response is equals to 1, which is Dear students, as discussed in the start of this chapter, mathematically total response of the system is equal to forced response plus natural response of the system, where on graph total response of the system is divided in two parts. First part is known as transient state and the second part is steady state. Students, whenever our system is at rest and the moment we apply the input to the system, due to this sudden changes in the response of the system occurs. This is known as transient state. And whenever these transients get settled down and the system starts working normally, is known as steady state of the system. Students, now we will discuss significance of parameter A from transfer function of first order system. For the first order system given in the figure A, step input is applied and output in time response is equal to 1 minus e power minus at. Now to find significance of parameter a, we will find system response at time equals 1 over a seconds. If you substitute time equal 1 over a seconds in exponential term, we get 0.37. Now substituting value of natural response in total response equation, we get output of the system at time equals 1 over a second equals 0.63. Now if you look at output equation for this system, which is C of t equals 1 minus e power minus at time t equal to 0 seconds, system response is equal to 0. And now if you analyze response of the system at times t equal infinity, the total output of the system will be equal to 1, which implies that final output of the system is 1. Dear students, from the previous slide we studied that at start or at time equals to 0 seconds, response of the system is equal to 0, where at time equals to infinity, the response of the system or output of the system equals 1, which means that final value of the response is 1. Now we will define time constant. Time constant is the time it takes for the step response to reach 63% of its final value. We call 1 over a the time constant of the response. And the time constant of the system can also be defined from the output equation. The time required for the exponential term e power minus at to decay to 37% of its initial value, which is 0.37. Now time constant is represented by tau, which is equal to 1 over a seconds. Now if you look at the figure, which represents step response of first order systems, where time axis is divided into time constants against output of the system. After the time of one time constant or 1 tau, output is equal to 63% of the final value. After time equals 2 time constants, output of the system reaches 86% of the final value. After the time of 3 time constant, output of the system reaches 95% of the final value, and after 4 time constant of time, output reaches 98% of the final value. In this figure, delta represents final value of the system. Dear students, now we will study transient specifications of first order system. In these specifications, we have rise time and settling time. Now we will study rise time. Rise time is defined as the time required by the first order system in which its output move from 10% of the final value to 90% of the final value. Now for rise time, we will solve output equation of the system for value of 0.9 and 0.1. We will find the desired time and find the difference among two. If you see the figure which represents step response of the first order system, in this initial slope is equal to 1 over time constant, which is equal to a, and time axis is again divided on the basis of time constant. Now for rise time, we will find the difference of time for system output 0.9 and system output 0.1. Or mathematically, rise time will be equal to 2.31 divided by A minus 0.11 divided by A. And from this rise time is equal to 2.2 divided by A for a first order system. Dear students, second transient specification of first order system is settling time. Settling time is defined as the time of the system in which response of the system reaches and stays within 2% of the final value. For instance, final value is equal to 1, so the moment system response reaches 0.98 and stays within the limit, this will be known as settling time. For settling time, we will substitute output of the system, which is C of t equals 0.98 in output equation of the system. So we get settling time equals 4 divided by A, or this is also equals to 4 ta studied in previous slides. Or in simple word, settling time is the time the moment transients are settled down and system response is in equilibrium state or no changes occur. Settling time can also be verified from the step response given in the figure. The moment output of the system reaches 0.98 and after this system response stays within the limit, the first time system reaches 0.98, the time corresponding to this is known as settling time. Dear students, now in the given example we have a first order system for which we have to find time constant, settling time and rise time. Students, now in the solution, if we compare given transfer function with the one in figure A, which is A divided by S plus A, we know that A equals 50. Now time constant is equal to 1 over A or 1 over 50 and its value will be 0.02 seconds. Settling time is equal to 4 over A or 4 over 50. So settling time will be equal to 0.08 seconds. And finally, rise time is equal to 2.2 divided by A or 2.2 divided by 50. Here, rise time will be equal to 0.044 seconds. Now, if any of you have any questions, please ask.